Hi, my name is Brennan Zhao, my partner's name is Zhao, and today I'll be discussing the Mempodipper Linux local root exploit. This final project would not have been possible without Zhao's extensive research on the topic and creation of the final lab report. For me personally, I researched background information that's necessary in order to understand this exploit and video edited and finalized this final video in order to help you learn about this concept together. And before we begin, we need to review a few key concepts in order to understand what's really happening here. So just a little background info, we need to first understand what setuid processes really mean and what they do. So what is setuid? Setuid is essentially a security system where certain files, certain executable files have a certain privilege you need to be in order to execute it. And in order to do that, we sometimes need to run tasks as a user with a higher privilege than other accounts usually have, if we're especially running certain executable files that we need to do. An example, the su command can be used to log in as another user. And another key concept we need to understand is the stdir redirection. And essentially what this is that programs usually have two different output streams. One is stdout and one is stdir, which is stdout is the regular output to the screen, and stdir is the output of error messages. And this can be proven useful in order to separate the error outputs from our processes. But it can also be useful to gather all of the output in one place. Another thing we need to understand is Linux/proc file system, and this is the /proc file system. Basically, is it provides like a novel or like a flexible means of communicating between the user space and a Linux kernel. Basically, how an operating system can provide certain means of communicating the users to what the operating system, in this case the kernel, actually wants. And so more in detail, it provides access to various controls and data related to processes through an interface that, which is basically a file system, which is pretty cool. Last thing we need to discuss about is process ID within the /proc file system, or specifically the /proc/pid/mem. And this file, the /proc/pid/mem file, it basically provides a means of accessing the memory of the process running with a given PID of a certain file, process ID. So the kernel enforces the protection on this file to check that the process requesting read or write access has proper permission. But however, there's a clear security problem if any process on the system could read/write the memory of any user's process. So which in this case, that's a clear error, that's a clear vulnerability. So what is exactly wrong? So the mem function in the Linux kernel before version 3.2.2, when ASLR is disabled, does not properly check permissions when writing to /proc/pid/mem, which allows local users to gain privileges by modifying the process memory as demonstrated by Mempodipper. So when /proc/pid/mem is open, the kernel will call this code right here. And specifically, there are no restrictions on this opening. Anyone can open this /proc/pid/mem FD for any process, which is subject to the ordinary VFS restrictions. But it is simply, it just simply makes note of the original process self-exec ID that it was open with and stores this away for checking later during reads and writes. Writes and reads, however, have permissions checking restrictions. So specifically, there are two relevant checks in place to prevent against unauthorized writes: the check mem permission and self-exec ID. And what is check mem permission? Well, specifically is used by the kernel to check that the requesting process has permission to access the requested /proc/pid/mem file. And the code of check mem permission simply calls into _check mem permissions. And so here's the given code for that to the right. So there are two ways that the memory write is authorized. So either within that code, if you take a look at it, task == current, meaning that the process has that the process being written to is the process writing, or current, the process that is the process writing has esoteric ptrace level permissions to play with the task, the process that's being written to. So maybe you can think of like a trick. Maybe there's a way to trick the ptrace code, but let's try to figure out how we can make a process with write arbitrary memory to itself, so that task == current. So given in this, su will spit out whatever text you want onto stdir, prefixed by the unknown ID. So we can open an FD to /proc/self/mem lseek to the right place in memory for writing more, which we'll discuss more on that later, to use dup2 to couple together stdir and the memory fd, and then to exec to su to shellcode to write a shell spawner to the memory process memory, and then we have root. So here are the other restrictions that come into play. After it passes the task equals current text, is then checked to see if the current self-exec ID matches the self-exec ID that the FD was open with. So what on earth is self-exec ID? It's only referenced in a few places in the kernel, and the most important one that happens to be inside of exec. And here's the given code below. Self-exec ID is incremented each time a process execs. So in this case, it functions so that you can't open the FD in a non-suid process, dup2, and then exec to a suid process, which is exactly what we were trying to do above. We fork a child, and inside of the child, we exec to a new process. The initial child fork has a self-exec ID equal to its parent. When we exec to a new process, self-exec ID increments by 1. Meanwhile, the parent itself is busy execing to our shellcode running su process. So its self-exec ID gets incremented to the same value. So what we do is, essentially, we make this child fork and exec to a new process. And inside of that new process, we open up an FD to /proc/parent PID mem, using the PID of the parent process, not our own process as was the case prior. We can open the FD like this because there's no permissions checking for a mere open. When it is open, its self-exec ID has already been incremented to the right value that the parent's self-exec ID will be when we exec to su. Finally, we pass our open FD from the child process back to the parent process, doing our dup2ing, and exec into su with the shellcode. Objection, where do we write to? We have to lseek to the proper memory location before writing, and ASL randomizes process addresses space, making it impossible to know where to write to. This means that su does not have a reloadable text section, otherwise it would spit out dyn instead of exec. It turns out that su on the vast majority of distros is not compatible with PIE, disabling ASLR for the .text section of the binary. So we've chosen su wisely. The offsets in memory will always be the same. So to find the right place to write to, let's check out the assembly surrounding printing unknown ID error message. And here it is. It gets the error string here, and it writes to stdir, closes the log, and then exits the program. So naturally we want to write to that memory location minus the number of letters in the string unknown ID, so that our shellcode is placed exactly at the right place. The shellcode should be simple and standard. It sets the UID in GID to 0 and executes into a shell. If we want to be clever, we can reopen stdir prior to duping the memory FD to stdir. We choose another FD to dupe stdir to, and then in the shellcode we dupe to that other FD back to stdir. So here's the code, and next is a video demonstration on how to do this exploitation. Thank you.